We are... Va? Sì. Okay, so we are going to start. So please take your seat, and the chair of today afternoon is Dr. Aldo Ianni of LNGS.
Okay, please.
Hi. So hi. I'm asking myself what's the probability that anyone remembers something from a couple of days ago. Oops, that was very weird. Anyway, hi, welcome back. So we'll continue. The situation is really awful because I have many slides. We have a lot of material to cover, and we have limited time. So I'll tell you what what I'm going to do. So those 3 hours, almost 4 hours that we have together. So I'm trying to cover basic of statistics and probability, and also advanced methods, and also to give you things beyond. And material-wise, I think it's about 2 statistics classes, like 2 semesters, plus a colloquium in 4 hours. So it's definitely a lot of material. And my tactic will be as following. The stuff that's on my slide, you can download and look at it later. So I will try to explain things that I think that are more important. And worst case scenario, all the technical part, you can look at the slides and catch up yourself, because as I said 2 days ago, this is not the way to learn statistics, and there are books, etc., etc. So I hope you agree, because it's definitely not a democracy, and yes, so you have no choice. Okay, this is a funny photo I edited a couple of years ago for a conference about limits, and the talk was about how desperate people are to get lower and lower limits, because at least in the dark matter, I also know that in the neutrino world this is the case. So last time on Statistics Underground, titles. So we talked a little about the likelihood function just before we broke to the hands-on session. And I'd like today to continue where we stopped and talk a little about distributions. Many distributions. Some of them are here. We're not going to cover all of them. I will talk about 2 or 3 that I like the best. So we must start with the definition of Bernoulli trial. So this is an experiment where you do a certain number of trials of some event, and each trial has an independent probability for success or fail. It's independent from the previous event, but the probability is all the same. Let's say we flip a coin, so it's 50%, so we flip it again, doesn't matter what came out before, it's a new result. So if P is the probability to success, 1 minus P is the probability for a failure. And here comes the binomial distribution. This is a discrete probability distribution where you obtain exactly n successes out of n trials. Each trial has a P probability to succeed and 1 minus P to fail as before. And it's important to remember that in a binomial distribution, you must have n. So you know how many trials you're going to have. And this is the formula. It has basically 2 parts. This is just the number of permutation of getting n events out of n. And this is the probability. Yeah, I need glasses. Okay, and this is the probability. Our parameter, our random parameter is small n, This is what we're sampling, and big N and P, they are the parameter of the distribution. And we can also calculate the expectation value, the mean, and the variance. And again, this is all textbook stuff. So how the binomial distribution looks like. Here are a few histograms I generated. So X is the number that you get from the distribution. N, little n, is the number of successes. And in this case, we had 5 trials in a 50% chance. Here we have 10 and 20. And of course, you can see that the upper number here is always the number of trials, because you cannot have more successes than the number of trials. If we change group, okay, and here's some for comparison how it looks like for a higher and lower probability. So in the 50% probability, you can see it centers roughly, or here you can see it's exactly around the center. 0, 10, so it's here it's 5. Of course, it looks better as we go to more and more beans. If the probability is lower, it will to the side, to the left side. If the probability is higher, it's closer to 1, it will go to the right side. So nothing exciting here. Let's flip a Bayesian coin. This is a fun exercise that I also encourage you to try and do it later yourself in Python. So just to remind you, this is the Bayesian formula. We have 3 terms here. We have the prior, which is our knowledge a priori. So I'm very naive person. I assume that the coin I got is fair. So my prior will be 50%. Then we have the likelihood, which is the probability of observing whatever number of successes out of whatever number of trials. So this is what we saw before, the binomial distribution. And this Px is the normalization factor, which is just an integration over everything. We will put it aside for now, because if we're interested just in the shape, then it wouldn't matter. And after we multiply it all, we get the posterior, which is the result. So if we'll do it in Python, and it's very simple. It's like 10 minutes if you need to remind yourself how to generate the shapes. So let's see what I did here. Okay, so I have a coin that I flipped 20 times, and I got 5 heads, and I'm asking myself, is this a fair coin? It's a fair question. So the inputs that I have to my case, so the prior will be this Gaussian around 50%. This is my knowledge. And here I chose arbitrary width. Of course, the narrower my prior is the more certain I am in the information. This is the likelihood. And when I multiply them both, I get the blue curve, which is my result. And from here, I can deduce things. So just by hand waving, you can see that it doesn't look very fair, but it's not very strong statement, because the blue line is wide. What if I, instead of the prior, I'll take a thinner prior, like in here? So in this case, the red, the likelihood is the same. I just use a thinner prior, and the result I got is a thinner line, and it's more near the 50%. Why? Because here I say, okay, I have a coin, I flipped 20 times, 5 times it was head. That's one source of information. The other source of information is that the coin is fair as much as I know, and I know it pretty well because I put here a very narrow shape. On the other hand, I can say I have no idea about the coin and put in a flat prior, which is here. And obviously this will not change the likelihood. And as we said 2 days ago, even putting a flat prior is a statement. So it's not always the easiest choice. I could also choose other priors. Let's see what I put here. Okay, so this is a Gaussian with the mean at 0.3. So using this means that I think that my coin is biased. And what do we have here? Well, that's long. So we have 90% of Gaussian plus 0.1 flat. So this is another way to quantize my uncertainty here. Next, Poisson distribution, we all know that. So if we take the binomial, take number of trials to infinite, and assume that the probability for an event is small, and we'll talk what small is in a second, then we get the binomial distribution. It's a nice math to do, not in Python, but on a piece of paper and pencil to try to get the Poisson from the Poisson from the binomial. It's something that I think it's worth doing at least once in your life. So it's once in a lifetime experience. Yeah, so that's the Poisson distribution and the expectation value and the variance. And here you see how it looks like for various input parameter, and there's the sum. And I have nothing more to say. And let's just do a silly example. Let's assume that I get emails at rate of 10 messages per hour. It's reasonable. And this is a Poisson process. What's the probability of me getting exactly 10 emails in the next hour? So I take the Poisson formula, I put in the numbers, and as opposed to the binomial distribution here, I don't have I don't know how many trials I'm going to have. I know that there are going to be many trials, but I don't have a finite number. So if you put the number, you will get 12%. And then you can ask yourself, what's the probability of me getting no emails in the next hour? So I'll put the 0, and I get a very small number, which means that it's very small. So often in textbook, the first and sometimes the only example they give to a Poissonian process is a nuclear decay. Why? Because it's very binomial, right? It's two cases, either the nucleus decay or it's not. The events are independent. We know the mean rate from the half-life, right? This is this gamma. And two events cannot occur at the same time. So it's a very good binomial process. However, what I do not know is n. This is why usually we will not use the binomial. Then we use the Poisson. So it is a Poisson process only if the number of nucleus is big enough. So it means that or the decayed nucleus can decay again, so it's not disappearing, it's just always there, which is nonsense. Or the number of nuclei is large compared to the decay rate. And this is an error that sometimes we do just without paying attention. We just put the numbers in the distribution without checking if it makes sense or not. And here's an example to an unfortunate case. So two radioactive sources, cesium with a long lifetime, and rubidium with a short lifetime. And I'm asking myself if I take such sources, I repeat the experiment many times because I want decent statistics. I want to measure how many decays I'll have over 1 hour. So for the cesium, it's pretty straightforward. I know that the number of nuclei at the beginning was 50 times 10 to the 12th. I don't really need this number. And then I can calculate how many nuclei decay, and I get 130 millions, which is much less than this number, which is great. However, for the rubidium case, with a very short half-life, you get that the chances of a nucleus to decay each second is this number, which means that in the 1 hour I'm asking about, 30 times 10 to the 9th nuclei decayed. Now, it's a great number. The only problem is that in the initial sample, I only had like about 10% of this. So this is a case where the Poissonian distribution will not work because the conditions are not met. So obviously, you can also see that the 75 seconds are like 50 half-lives. You get 50 half-lives in 1 hour for the rubidium, so this is definitely not a good thing to do. Another important example is a trigger rate. And you heard about experiments yesterday, and you saw the technique of veto, which means that you use an event happening at several detectors in the same time in order to reject background. So let's see the statistics behind this. And this is an issue that many people do wrong, this calculation. So that's why I'm taking the time and walking you through it. It's 3 slides. So slide number 1. Let's assume that you have a single PMT and it trigger at rate gamma. Each trigger, when it gets a signal, each trigger is tau seconds long. And all the triggers that arrive in the time window are counted. So for example, if here the red marks are the events, here I got an event, I start counting and I have 1, 2, 3, 4, 5 events in my time window. Second time window, I have 3 events. Here I have 1, 2, 3, 4 events, and so forth. So the expected number of hits in time window tau is simply the rate times the time window. The rate of it triggering n times in this time window is the rate of a single trigger times the probability of getting n-1 triggers following. So here, the units we want to get is not number, like before, or probability. Here we want rate. So that's why we do it in this way. So we have here probability, or the rate for 1 decay, times the probability of n-1 in the Poisson, and you put the numbers, and you get this. And when you plot the results you get those colorful curves, and this is the values of the parameter. So the blue line, for example, is a short time window and a short rate. The green, the green is a longer time window with the same rate. You can see that with the longer time window, you get more events, and it's about 10 times more as you expect. So the longer the time window, the larger n is going to be. You can also see that the faster gamma is, the more triggers you get, and everything makes sense. Let's take it a step forward. Now I want to check the rate of n hits over m PMTs. So in this scenario, we're also counting hits. So each hit is a number. So if a PMT got 2 hits in the same trigger window, it will be counted as. Now that's where you need to say 2. Let's try it again. If a PMT got 2 hits in the same trigger window, it will be counted as 2. Thank you. Yeah. So let's do the calculation. A PMT triggers at rate gamma hertz. So the rate of a single hit over all m PMTs is m times gamma, like before. Now we can go through the calculation. It's really technical and boring, but we can also say that this is very similar to the previous slide, but here, in case of having one PMT triggers at rate gamma, we have one PMT triggering at m gamma, because it's basically the same scenario. We got a hit, we start counting, tuck, tuck, tuck. I don't care whether it happened on one detector or not. So all I have to do is, instead of gamma, put here m gamma, and I get the result. And again, if you do not believe me, please do the math. And if you still do not believe me, go and simulate it, because it's a nice simulation to do. And finally, this is where we wanted to get to. Now we have rate of m PMTs over n PMTs. However, in this scenario, we are counting PMTs. So if a PMT got 2 hits, it will be counted as 1. This is where it makes a difference. So like before, a PMT triggers at the rate gamma hertz. The probability that a PMT did not trigger, so that's the opposite one, is the Poisson of a 0, which is exponent of minus mu. The probability of exactly m PMTs triggering, like before, is the probability that m triggered and n minus m did not trigger. So here we use the binomial distribution, and we have this one. So we have here n, we said n did not trigger. Now we say, what's going to, yeah, I got here the index wrong. So this should have been m. So the probability is this is m times, and this is m minus n. N minus m, n is larger, yeah. Yeah, that's the probability of exactly having n out of m. So if we use m gamma, which is the rate of a single hit over m PMTs, and we put everything together, so we have here the probability of a single hit times the probability of getting exactly the number of hits that I need. And notice that here it's n minus 1, because the first hit is here. And you get the following result. And again, go through the math and pay attention to the indices, unlike me. And here's the magic of vetoing or coincident. And for a detector that triggers at about 3 kilohertz, which is, it makes sense as a dark noise rate. And for different number of coincidences, so here I have 100 PMTs, and this is the number of coincidences that I want, and this is the time window. So you can see that if I start with the 3 kilohertz rate, the minute I ask for coincidence of 2, it drops. And it drops very sharply, right? Coincidence of 7, let's say, is already many, many orders of magnitude less. Yeah, this is just the same. I won't get into this. Okay. Another nice exercise to do is to find out that the time between triggers in a Poisson process is an exponent. So when you, I don't know if today, should we do the math or not? Let's not do the math. But anyway, if you check how much time passed between each triggers, you get something that's distributed exponentially. And this is, of course, the exponent distribution. And the important thing about the this distribution is that it's memory-less. It's the only distribution, at least I know, that has this capability. It means that it doesn't matter where you start. It's always, if you move forward, it will be always the same probability. And this leads us to a funny paradox, the waiting time paradox. So it goes like this. You come to a bus station, the bus comes every 10 minutes. And let's assume that it's a Poisson process. Real buses are not Poissonian, right? Because there are other considerations there. But let's assume that this bus system is Poissonian. And you ask yourself, how much time will I wait for the bus? And let's assume that you came right after the bus left, and you say, okay, I'll probably have to wait about 10 minutes. What will happen if you come 9 minutes after the bus left? Now, you would expect the waiting time to be shorter, but it's not. It's still 10 minutes. This is, it's called the waiting time paradox. Of course, not paradox. You can calculate it or you can simulate it. And also, it's a nice exercise to try and simulate it. I mean, it's nice not just because it's proving this point, but also as an exercise in doing such simulations. And finally, our best friend, the Gaussian distribution. So we had the binomial, then we had Poisson. Now if we really get crazy for large number of events, we get, from the Poisson, we get Gaussian. We all know the Gaussian distribution. Important thing to remember is the z-score. Now the z-score I can do on the Gaussian, which is just the value minus the mean divided by the width. And this tells me how far away I am from the center in units of sigmas. So that's the famous 1 sigma, 2 sigma, etc., etc. But you can also do it in other distributions. Just by doing this shift, of course it will have different meanings, but this is still something that can be done and is done. There's the cumulative distribution that we will meet later a lot, and it's marked with the phi. And the value of phi at a certain z, like say here, is the probability to have something below it, just because it's an integration of everything. And obviously 1 minus phi is the other side. That's all I have to say about this. The z table. So this is how, if you're not near a computer, this is how you go from a z value to a probability. So just to remind you how it's been done. So the probability of z being lighter than 0 is half. It's not really, you don't need a table for that. What's the probability for z being less than 0.44? So it's phi of 0.44. You go to the table. You say, okay, this is 0.4, 0.44. So this is 67, which is this 67. The probability of being above 0.44, it's just the 1 minus. And you can do a funny calculation, like ask yourself what's the probability of being lighter than minus 0.44, and then you start to think how to reconstruct it. It's a combination of the numbers we had and the half, and you get some number. Okay, let's do a quick example for the Gaussian. So we have a company that's doing aluminum foils with a mean thickness of 100 micrometers and a standard deviation of 10. What's the approximate probability that the foil will be more than 120 micrometer thick? So 120 micrometer is 2 sigmas away, because 120 minus the mean divided by the sigma. And the probability of having z larger than 2, which correspond to our situation, is, you get it from the table, and it's 2.3%. Again, we need to be careful about when to use the 1 minus and when not to. Also depends at what table we use. So what's the probability? A sample of 25 foils will have an average thickness of more than 25 micrometer. So this is like a step forward in difficulty, but still it's the same idea. We know that the standard deviation is 10, but here we have a sample which is limited in size, so we have to put this into account, which is the square root of the number, so it's 10 over 5, which is 2. And again, you put the numbers in, and you get 0.62%. So the reason I'm putting these exercises, I mean, this is like high school, I think, maybe. It was a long time since I went to high school, but this is undergrad level. But still to give you an indication of how things are feeling like. And the reason that we love the normal distribution, I hope you love it like me, is the central limit theorem, or the CLT. It's a very, very cool feature. It means that the sum of independent random variables will be a Gaussian. Now, it's really, really strange, but it's working. And again, I encourage you to do this simulation. It's really the best way to understand the meaning of things. So, what did I do? Okay. So if we take one distribution, so on the left side, you see an exponent distribution that I chose, and you check its mean. Then you do it again, and you again check the mean, and again, and again, and again, and again. You will end up with a perfect normal distribution. And this is very important in statistics, and it doesn't matter what sample you will get. You start from. And you can see slowly how it's becoming more and more normal as we go on. And here's just another example with a flat distribution. It's really cool. A few words on Monte Carlo. So Monte Carlo is numerically generating random data sets, and it's usually done on a computer. I tried to do it with the dice once. It's really boring after 1,000 events. So what we need to, in order to do simulation, we need obviously a model because we need something to simulate. Then we need a random number generator, but we don't want it to be too random. Why? No idea? Yeah. No. It's really, it's very trivial. So the reason is that you want to cross-check yourself. You want to be able to repeat exactly the same universe if you want to. And my advice to you is when you do simulation, always check that you do the seed correctly. Because sometimes it happens, a person runs many simulations, then he or she noticed that they forgot to initial the seed, so all the collection of files they have are exactly the same copy of the first one, which is a huge waste of time in disk space and CPU. Okay, so we have a random number generator, and we need a sampler. A sampler is a tool that takes a number from the random generator and moves it to the distribution that we want. So computers know how to do a flat random number, but we want a certain shape. We want a Gaussian or exponent or whatever. So there are many ways of doing it. I'll quickly go over 3. The first one is my favorite. It's by applying the physical process. So let's say you want to do a Poisson simulation. So we already know that Poisson happens when we have random events in constant rate. So what we have to do is write a loop. Each instance of the loop is a time window. We take a random number, we pick a random number. If it's under a certain value, we count an event. If it's not, we don't count, and this will give you a perfect Poisson process. And if you want to do exponential, then just take the time difference or the counter difference between two events, and you'll get exponent. Second way is the inverse transformation. So again, I'll go through it quickly. It's very technical. It's not hard, but if you care and you want to really understand, then go back and review it slowly. So what you do in this case, you use the cumulative distribution. You take the cumulative distribution and you inverse it, so you take out the y. And if you think about it, the cumulative distribution is actually, it's breaking our distribution to equal steps. But when you look on here, on this side, so this is the cumulative of this. And here, this is like the 0.1, 0.2, 0.4. By definition, each slice is equal thickness. So I'll take this, I'll shift it 90 degrees and flip it, and this will give us the way to generate a flat y into an exponent x. So it's working nicely. It's relatively fast. However, it's not always feasible because it requires, you need to be able to transform the function. The third option, anyone play darts? Play darts? Yes, no? Help me, I'm trying to wake you up, right? Who plays darts? Yeah, okay, thank you. We need some sort of, give them like bonuses or peanuts or bubble gums, I don't know, something like that. Okay, so here is basically the dart method. So for example, if we want numbers inside a circle, we'll draw a circle. We'll start randomizing numbers in the R over R space, 2R over 2R space, like this. If it falls in, we keep it. If it falls out, we do not keep it, and we get the distribution we want. The other example for this specific case is to do the variable transformation. And here again, I remind you to be very careful here. It's very easy to do naive mistakes, because we all think, okay, that's easy just to do this transformation, right? You did it gazillion of times. But we have to do it correctly, and remember that it's not linear, that we have this R square thing. So we cannot just take random R between 0 and R and random theta between 0 and 2 pi and get what we want, because we will get this, not this. So you have to do it correctly. Okay, part 3, estimation. So estimation is getting the information we want out of a measurement and transforming it to a number. So we draw some random variables from a PDF, which is our experiment. And the PDF is characterized by a parameter, theta. So it can be the width or the mean. The estimator for theta will provide an estimate for theta. That's a great sentence, right? The estimator for theta will provide an estimate for theta. It's strange, but it's true. So the estimator, what it does, you put the numbers in, and you get out a value, which is the estimation to the parameter you want. So, for example, if you do it for, let's say, classical exercises to do it for a Gaussian, if you do it for, let's say, a Gaussian, you'll get the estimator for the mean is this thing, which is the average. right? So we got that the mean is the average, which is obviously correct. But keep in mind that while the left side is the truth or the actual value, the thing on the right is the estimation, which usually will not be exactly the same value. We already know that it will be dancing around. Now, this estimator, this thing that take the numbers and move them into an estimation, it's a way to quantify our experiment. We'll soon see that the likelihood, maximum likelihood, is an estimator. And we want those estimators to be nice. What does it mean, nice? First of all, we want them to be consistent. By consistency, I mean that it will be close to the nominal value as much as possible when I take it to infinity. So if the more information I have, the more accurate my estimation would be. We also want it to be non-biased. This is just an offset. So there's some similarity between the two, and though it's very hard to find a consistent estimator that's biased or a non-biased estimator that's non-consistent, it's still possible to find such. So they're almost the same, but not exactly. Then we have the efficiency. Efficiency is talking now about the width. We want it to be as efficient as possible, so it means that it will be narrow. Because this, the green estimator is giving the same value as the blue for the mean. They have the same center. But the green is so much wider, so it's less accurate, and we call it less efficient. And we'll see that there's a limit to how efficient we can get. It's a good sentence to tell your boss or your parents, there's a limit to how efficient I can get. There are also other properties that we won't discuss, robustness, the simplicity, and et cetera, et cetera. Remember this? So this is the exact same slide that we saw last time. So this is the likelihood function. I'm reintroducing it. So it's simply the multiplication of all the PDFs. And this gives us a number that tells us how well those numbers agree with the assumption I put in. So for example, here the assumption is the mu value. And they agree the most for the mu value that I actually generated them with. Maximum likelihood estimator is taking the maximum of this value. Now we move it to log scale because we have multiplication and it's nicer to move it to sum by logging. And we move it to minus just because, first of all, it's negative numbers, so it's nicer to have them positive. And also in this way, we can minimize the function. So it's usually a minus log. So the game plan is as following. We take n measurements of random variable x. We have some model, and we test whether they agree or not using our PDF or probability function. We minimize it with respect to our parameter. If we can, we just do it with a pencil. We calculate the derivative. If we cannot, we do it numerically. And the lowest point is the most probable value. So in this case, this is the most probable value. And the width will be given by this parameter. And we'll soon see that it's correspond to a certain value that we jump on the value of the minus ln L. Maximum likelihood estimators are usually consistent. They're usually biased, but the good news is that it's getting better as we have more and more data. And in the asymptotic limit, the estimator is efficient. The asymptotic limit means that we have a lot of events. Plus, there are also some conditions about the shape of the function. It should behave nicely. And then we get a limit to the variance, which is standard deviation squared, which is the second derivative of the log function using the parameter that I'm looking at. And this statement is just flashing this term so you'll know how to relate it. It's based on something that's called minimum variant bound, or MVB. And it says that there's a best case estimator. So you can also go to the textbooks and follow how it's how you reach it. The value here, is really the best one. The not so best one is for a biased estimator, for example. It looks like this. Okay, what about the uncertainty? So you have 4 options to estimate the uncertainty. In some cases, if you can either say that you're lucky or that you have a boring function, you can calculate it analytically by doing the integral and calculate the expectation value of theta square, and then take the square of the expectation value of theta, and this will give you the variance by textbook. Option number 2 is do Monte Carlo. So you simulate many experiments with similar statistics. You collect the mean value, and the more information you have, the better estimation that you'll have for the width. There's a thing that's called asymptotic normality, and it means that the maximum likelihood estimators for large sample, you'll get approximately a Gaussian that we previously saw already. Now, a very gentle practical point. Why do I encourage you to try things yourself? It's not just that you'll get the plot and you'll say, yeah, I got a plot. Apparently she was right. It happens. It's also that you'll discover all the delicate points. And there are always delicate points that you realize only when you do it. So, for example, let's assume that you want to test number 2. You wanted to see if it's working, and you want to generate this Monte Carlo sample. What value will you use when you generate the sample? Will you use a truth value or the expectation value? What about the sample size? Let's say that your sample size is 50. Do you do all your samples 50, or you do 50 plus minus square root of 50 with the Poissonian uncertainty? What happens when the parameter is near its limit? Let's say it cannot be negative, but it's very close to the 0 line. How do you handle it then? So these are all very relevant questions, and you only think about them when you do the simulation. Option number 3 to estimate the uncertainty is using the information inequality. And that's true not just for the maximum likelihood estimator. And there, for efficient unbiased estimator, you can take the second derivative of the likelihood function, you put the theta value you want, and you get your variance. This is something also very useful, especially for cases when you have analytic functions. And option number 4, which is the reason why I took you through all the first 3 reasons, is the graphical method. So what we'll do, we'll take our log likelihood and we'll put it into a Taylor series. So that's the first term, then we have the derivative times the linear, and then we have the second derivative times the square. And but we want to do it all for the value of theta that we want. So the first one will be just the value, the log of the value that we want. The second will be 0. Why 0? Because by construction, theta is theta hat. Theta hat means it's the minimum. So I put here theta hat, this minus this, 0, let's go. And the third part, I'm using this information inequality. I'm putting it here, and I get this, this term. Now, if I'll put theta equal theta plus delta theta, you will get minus half. Now, this minus half is super duper important, because if you look at the likelihood curve, and this is theta at our minimum, this is ln of the minimum point. It means that if we'll go up by half, it will give us the 1 sigma. Once we project it on the theta axis. And we can do the same for 2 sigma, and it gives us minus 2, etc., etc. So this is very useful, and this is why you usually see 2 ln or 2 log likelihood, because that's give you the 2. Keep in mind that the theta plus and the theta minus do not have to be the same. Usually they're not the same. The uncertainty to the left and to the right, but with good statistics, and if it's well behaving, you will get a parabola, and then if you heard the term Asimov data set, and everything start to get really crazy. So for example, here's a log plot of a likelihood function. So here the mean is at 1.062, and I want to check the 1 sigma, so I take a step down of a half, I do the projection, and it gives us the values that we need.
I'm sorry. Before we continue, I think we can take a few minutes for questions. Before you change subject.
Yeah, actually, if I made like 2-3 more slides, and then it will.
Okay.
I will
as
end.
you wish.
Yeah, but that's a good idea. Thank you. Okay, a few more words on the likelihood function. So far we just used the PDF, the probability, but we can use more information. We can add to this likelihood, which is just the PDFs multiplied. We can add the number of events that we expect to get, and this will be Poisson distributed. So I take what I had before, I multiply it by a Poisson. I do some shuffling, and I get the unbinned extended likelihood. Now I can take it and do a log. So this exponent gives me the minus n. This gives me the n factorial. Now this is a constant number, so I don't care about it. It's just a constant offset, so we'll just forget about it. Yeah, the multiplication is this, etc., etc. And you can bring in this one, put it with this, and you get the unbinned extended likelihood. And to find the minimas, again, you do the same. You take the derivative in n and in theta and in all parameters that you have. And if you take the derivative with n, you get the amazing result that n equals n, which means that the number of events you got is the best estimator you have to the number of events that you expect to get. You can also do it, this should be binned extended likelihood. So here is the same idea, but we bin it. It's also a very important example. Please find it in textbooks. I decided not to go through it here. So in the bin case, so if these are your events, you just divide it to bins. So for example, in this bin you have 0-ish. Here you have just a few. Here you have many. So apparently this plot do not correspond to this plot, but let's pretend that it does. So you do the projection by bins. The number of entries in each bin summed will give you n. And you can do the likelihood in the very same way. Some other useful extensions to the likelihood function include the following. You can do model combination, which is here. So here I have the Poisson like before, but I have here 3 parts. I have a Gaussian part with some nuisance parameter. I have another Gaussian part with other nuisance parameter, and I have some exponent. So this is just something I made up. Of course, there are infinite possibilities. And of course, the normalization constant, those alphas, you don't need all of them, because obviously one of them is just 1 minus all the others. So you can do model combination. You can use also additional data sets. I just use one. We can use calibration data sets as well. So here, for example, I use 2 data sets. So that's the first one, as before. And here's another one. So let's assume this is on our real data, and this is on our calibration data. And we can use this term to learn something about some of the parameters that are here. We can use it to constrain the parameters. Another thing we can do with our likelihood function is to artificially enter constraint to a parameter. And that's the yellow block. And in this case, I'm just taking distribution and I put it in the likelihood with a given sigma, and that means that this value will be constrained. And of course, you can mix and match. You can do all sorts of possibilities, model combination with additional data sets and parameter constraints, for example. We will see example. So now I will, it's a better point for me to stop for questions, if there are any.
Okay, very good, thank you. So, okay, please.
Thank you. I'm Mattia from Cagliari. I have a question about the relation between the chi-square definition and the likelihood, because usually we say that the chi-square is minus 2 the logarithm of the likelihood, right? In general, the chi-square is related to the likelihood.
You mean by chi-square, you mean the fit?
Yes,
Yes, you can prove it by likelihood function, yeah.
But it applies when the chi-square is Gaussian. But for example, I had to deal with a Poissonian definition of the chi-square. In that case, it is not necessarily, that relation does not apply. I mean, for example, when you showed a slide with the what about uncertainty, the fourth method, there was that relation was explicit when you wrote one equation. I mean, but we have to deal with chi-square definition which are not Gaussian, that relation is not necessarily true. The relation of
when I say chi-square, I meant the classical chi-square test. There are many goodness of fits tests.
Okay, this was just this clarification. Oh, thank you.
Thank you for the clarification.
Any other question? Just let me take you the microphone.
Hello, I had question. You said that usually the maximum likelihood estimators are biased, but like why is that so?
I'm afraid I don't have an intuitive answer. I can send you to a textbook to see the proof. You just
Okay, thank you.
And please, as we continue, if you have questions, feel free to raise your hand and ask. It's
Any other question? So in the meantime, I ask a question myself. This issue concerning the bias, I think it's a tricky one that also how one realizes that there is a bias embedded in the likelihood. By Monte Carlo, comparing the prediction with the likelihood built on the data. I don't know. It's because if there is a bias, this is a systematic that maybe one has not under control.
so. Bias is actually a systematic that we like because it's something we can correct for. If we know that we have a bias in our estimator, and a bias is a constant offset, then I can just correct it in my formula. And I know about it from either simulation, or you can get it from calculation, or when you take an experiment and you see that something's off. Depends how complicated the thing is. I think the most famous bias is there's the standard deviation, and there's sometimes there's the n-1 thing there. Do you know what I'm talking about? Mm-hmm. Sometimes you divide by n, sometimes you divide by n-1. So this is an example for a bias correction. And again, you can go to textbook and at least all the basic textbook I know go through the math. So you know you have a bias, and you introduce this correction. So that's actually something we can live with, and for if you really like it. Yeah.
Okay. In addition, also, I think the questions that you made in this highlighted section of one of the previous slides before you started I think those are important. In particular, the one concerning no, one more forward. These ones, yes. I think the question concerning or identical sample sizes or using the Poisson, I think that is an important one, because as a matter of fact, you have used that in the definition of the extended maximum likelihood, introducing this factor which
Poisson, yeah.
Which I think is the right thing to do, to use, right, as a matter of fact, the extended likelihood, because the number of samples that you have got from your experiment is just a representation of the real situation. And so that is a random variable which should be parameterized right, using these Poisson statistics.
Yes. I intentionally said it as questions without giving the answers, because I wanted to maybe intrigue people to look for it themselves. But I'll tell you the answers. Here I would say truth, but with the distribution around it. And here, yes, you definitely need to not to do a fixed size samples, but do the variation. And this is especially important when you want to do in the inference. We will not talk a lot about asymptoticity, and when you're trying to check whether things are really asymptotic. And there, if you do not do it right, then it doesn't work. And, okay? Any more questions?
Yes.
Hello, I'm Leon from Zagreb. I have a question about the bias and the consistent estimators. You mentioned that if the bias is just an offset, how can a biased but consistent estimator still give a correct value? I think it was somewhere written.
So bias you can usually correct. Consistency, the main point here is that it gets better with more information. So they're pretty much, they're not exactly the same. I mean, they seem the same because it's all about an offset, but in consistency, it's the more statistics you have, the better it will get. And in the bias, either you know about it and you correct for it if you can, or you're stuck with it.
So if we have a large enough sample, then the bias is irrelevant because it will correct itself?
So usually not. I mean, it depends again in the definitions, or I'll answer it this way. If it's going away when you go to higher n, it's not a bias. Because bias is something that like a bone in your throat, right? It's there.
Okay, thank you.
Any more questions? Yes, no? Okay.
So if not, we keep going. But in any case, as the speaker asked, if anyone has a question, please just ask and I get you the microphone, okay? Okay, thank you.
Thank you. Okay, so we talked about those crazy maximum likelihood functions that get uglier and uglier, which on one hand it's great because I have more information in, on the other hand it's more complicated. So if I want to take the derivative and find the minima, suddenly I cannot do it with the pen and paper. I need to simulate it. So usually when we want to minimize complicated likelihood function, we'll use simulation. Not simulation, just scanning. We can use minimizers, but they're only partly helpful. First of all, because we don't just want the minima, we want the entire behavior. And second, it's very easy to get lost in a minimizer. I've talked in the previous lecture about the black boxes. So minimizer is a great example to a black box. Put a number in, hit enter, you get a number. You need to check whether maybe it's a local minima and not the global minima. Maybe it didn't converge. Maybe something strange happened in the minimizer. So use minimizers with caution. And another bad news is that the more information we have, the larger is the uncertainty. The likelihood curves will become wider and wider. And again, if you do not believe me, just simulate it. So let's look at the likelihood function again. And remind me, why are we doing this? Why are we here? Not just for the food, pasta. What do we want to get out from this likelihood function eventually? Let's say you're looking for dark matter. There's a lot of letters here. I'm sorry, it's hard for me to understand with the mask. We want to get the best estimate for parameters. Yeah, but be more specific. I have here a lot of parameters. Which one do I really care about? So any guesses? What do I need to calculate rate? Right, because I use rate to calculate cross-section. Once I will know how many dark matter events I had in my sample, I can calculate the cross-section. So what do I care about here? Yes? Which is n. So I have all these parameters. I don't care about them really. They're just a tool. What I really want to get out, to get from this is n. And here's an example to minimizing cycle. So here are two parameters, and yeah, I look for the minimum, and yeah. So I should have said that before. So we're doing this in order to estimate n. We don't really care.
What you mean is that the other parameters will combine together in such that n compares as much as possible with the set of data. If you have 100 data,
I'll answer. My next 10 slides are about those parameters. Okay, so what's going on here? So these are the parameters that I'm interested in. In this notation, it's also alpha s is the fraction, but usually it's one parameter. So I'm really interested in the number of new events that I have, my discovery. The Nobel Prize is there. An important comment. I'm happy that I actually added it to the slide because I knew I'll forget to say it, and I reminded myself. What we are actually interested in is, for example, cross-section, if you think about the limit plots. It does make a difference if you do your inference on n or on cross-section. It's very easy to do this mistake and do the inference on n. It's the easy way to do, but it's not completely correct. It's not a huge difference. I'll show you an example. So this is just, we'll say n, but it's just a kind of simplifying thing. All the other parameters that we'll call theta are nuisance parameters. They're there. I need them, but I wish they'll go away. They just make my life more complicated. And we call it parameter of interest, and we'll mark it with the mu, and nuisance parameters will mark it with the theta. And now I'm proud to introduce the profile likelihood. Anyone did a profile likelihood analysis before? Yeah, no? Okay. So what's the profile likelihood? So again, it's very wordy, but when you think about it technically, it's quite simple. So yeah, profile likelihood. So we said that mu is our parameter of interest. It can be one or many. Theta is the nuisance parameter, and x is the data. So lambda, I mark my profile likelihood ratio. And on the top, I have the likelihood of x, mu, and double hat theta. At the bottom, I have the likelihood of x, and mu with a hat, and theta with a hat. What it means is that at the bottom, I take the unconditional probability, which is the lowest point in my likelihood. So I do a minimization over everything. So in this nice, well-behaving example, it will be this point here. What I have on the top, mu is changing, and for each value of mu, I find the theta or set of thetas that minimizes it. So for mu, I will have, for example, this curve. So this curve is for a given theta equals 0 in this case, and I have the shape in mu. The curve here will be for mu equals something else, and I see how theta behaves. So that's the idea behind the profile likelihood. You need to find the absolute minimum, and then for each value of your parameter of interest, you scan for the other. How it looks like in action. So in In this case, we have the parameter of interest as a cross-section. You have it at the square up here. And I hope you can see with the resolution that this number is different than this one and different than this one. And for each one of them, I have a 2D figure of two nuisance parameters, theta 1 and theta 2. The color scale is the likelihood. So the purpler it is, the lower it is. So here with the star, I mark the minimum that I found. The circle is the nominal value, the 0 and 0. And you can see that it looks different. It changes. Also, the absolute value changes. So this goes down to 3, this goes down to 0, this goes down to 0.1. And if you'll notice, the x and y scale of the nuisance parameter is -1, 0, 1. This is because we used a normalized scale, because we use the penalty factor. So the 0, 0 is the nominal when there's no offset from the median. So that's the idea. I find my absolute minimum, and then for each one of those, I find the relative minimum. And this is like in live action. So there's a lot going on. On the left side, you see the value of mu that we sample. So here is 0, 1, now it's equal 3, now it will be equal 4, etc. And for each one of them, you see the matrix for the two nuisance parameters. And this is how you do the minimization. The lowest point is here. And then you have all the other points are relative to it. So that means the ratio. So this thing here is called the likelihood curve. It's super duper important. This is what you need in order to do inference. And there are two lines here. The red one is with profiling, the blue one is without profiling. And you'll notice that the one with profiling is slightly wider. Anyone knows why? You'll always have the one with profiling wider than the one without. Please? Guess. No one? When I add more information to my analysis, it means I add more uncertainties. The case without profiling is not that it's perfect and it's fine. I'm missing part of the information there. So it's more accurate, but it's less correct. So the more information that I add, the wider my likelihood curve will be. And now to a really, really cool thing that's called Wilks theorem. And this is something that's really important that you will understand correctly, because once you understand this, you understand profile likelihood. Yeah.
In the previous slide, so the blue line is the profile minimizing over all the nuisance parameters.
This one, the blue one is with the nuisance parameters set to 0, to their nominal values.
One is minimizing the nuisance parameter.
Yeah.
And the other one is setting all the nuisance parameters
To some value.
To the minimum.
To the nominal value.
The nominal means the one that you obtain minimizing the overall likelihood.
So no, so this nuisance parameter theta 1. So I'm saying it can be between -1 and 1, and the mean is at 0.
But 0 is the value that you obtain when you minimize over the old parameters.
No. This is the values. The units of this is in the units of theta. So this is some parameter, let's say it's in...
Just to understand, so here you have two parameters.
mhm.
One, you are considering a nuisance parameter in the profile likelihood.
Here,
One of the two.
here I have 3 parameters, 2 nuisance parameter, and
You have 3 parameters.
yes, yes. Theta and theta are nuisance parameter, and this one is parameter of interest.
So what you call nominal is...
Okay, I'll give you an example, okay? Let's say I'm doing a profile likelihood analysis of, I'm measuring the time it takes to objects to fall. And I'm using G. And my first measurement, I just use G equals 10. Because that's the value I got, yeah, G equals 10. That's the nominal value. In the red curve, I'm using G equals 10 plus minus 2. So I'm adding some uncertainty on G. So when I say nominal, I mean the mean value or the expectation value of some constant.
No, at least I understand. Just asking whether these nominal two values are the ones that you obtain when you minimize over the 3 parameters.
Not necessarily.
Not necessarily.
No.
It's just to show the difference when you fix them and it's not correct. And when you fix them.
No, that it gets larger.
Okay, Wilkes, Professor Wilkes. Okay, that's important. It's a little confusing, but again, it's like it's the delicate point you need in order to understand all of this. So even if you didn't follow exactly until now, try to understand this point, because later when you'll read it in a book or something, it will be easier to grasp, because this is the key to everything. What Mr. Wilkes said is the following. The distribution of Q, where Q is minus 2 log lambda, the distribution of Q evaluated at mu approaches a chi-square PDF asymptotically. What it means is that if I'll take this value, put here data that agrees completely with the hypothesis that I'm testing, and see what I'll get, it will be a chi-square distribution. The way to do it, for example, if you want to try it yourself, and again, I encourage you to try it yourself, you pick a model, you generate a lot of Monte Carlo experiments using this model. So let's say you did a model of 100 points distributed Gaussianly around 10 plus minus 2. Now you take those 100 points that you generated and you calculate the value of Q for those points using or testing the same hypothesis that you actually used. So you use a Gaussian with 10 plus minus 2. You get a number, you put it in a histogram. Then you do it again for another Monte Carlo sample. You get another point. You put this point again in a histogram, and again and again and again and again. Eventually, you'll come up with a chi-square distribution. And to be more precise, the degree of freedom of the chi-square is according to the number of nuisance of parameters of interest that you have. So if you have one parameter of interest, you'll get chi-square distribution with 1 degree of freedom. Yeah, so this is super important. And it's a little confusing because we're moving to different units now. Because this one here, the x-axis is Q. And the y is the number of times we got this Q value. So it's like a PDF of Q. And why it is important? Because if we know that we get a chi-square, we don't need to run all the 1,000 simulations. It means that when I'm doing experiments and I want to test some hypothesis, I can, and I'm using a profile likelihood, I immediately know what my distribution is going to be. So now I take my data set, I calculate, I get some Q value, and I know that this Q value should be evaluated on a chi-square distribution. So this automatically gives me the all I need to know. It's super, super powerful, and it's working usually most of the time. Any question? Okay, so I encourage you to go back and try to understand this using my slides or using textbooks, because this is the key to everything. It's super wordy, but once you got it, it's like riding a bike, right? It won't leave you. It hunts you in your dreams. Yeah.
You said that it works most of the time. So when does it not work?
Okay. Part of the time. So it's not working when things are not behaving nicely. So for example, when you have nuisance parameters that are limited on one side. Let's say you have something that's very close to zero but cannot cross zero because it's not physical. Then things will start to break, for example. If you have few events and in the likelihood function you end up reducing events from, like reducing background events, right? What happens when you estimate a negative background? Right, and then or there are all sort of crazy things like this. The way to handle it, it's very simple. You need to know that you're in the right regime. So once in a while, take a break from the flow of your work and test that it's behaving like this. Generate 1,000 samples. Sometimes it's very heavy on the computation because the model is complicated. But take the time and see that you get the chi-square back. Especially if you have all sort of crazy parameters. Okay, so previously I mentioned that it's important if you take the cross-section or you take n number of events. So this is just an example of the difference that it makes. This is the same data set, same everything, only here is number of events. And here is the cross-section, and just see that the shape is different. So when you do the inference, you can get different results. So that's just, I'll just wave it and go on. Do you know these comics? So this is like the comic relief that I planned. So my question to you is why is it funny? I mean, what's the punchline here? And then the second question is why it's not correct. So there are two physicists here, and they have a neutrino detector. And obviously the sun emits a lot of neutrinos, and let's say the sun exploded, so the neutrinos will stop coming. And I'm using my neutrino detector to estimate this. So, but my detector has some error, and this is the two dice. So if the two dice come up with 6, it will lie to us. It will give us the opposite result. So there's a chance 1 to 36 that it will give us false result. And then we hit enter, and the machine tells us the sun, no neutrinos, the sun exploded. So the frequentist says, well, the probability is exactly 1 over 36, and it's more than the 95 confidence level. I'm sorry, my friend, sun exploded. The Bayesian, however, is using the prior knowledge, and he says, well, it didn't. So it's funny because obviously the sun didn't explode, right? And it's kind of making fun of frequentists, which is not funny if you're a frequentist. But why is it not correct? I mean, obviously, right? It's the frequentist here did a bad decision. He's a bad frequentist. What did he do wrong? Yes. Oh, so can you?
I'm not sure about this one, but shows a certain probability threshold, which was basically just a person, how's it called? Internal choice. Basically, he's the one who chose.
It's more simple. If I understood you correctly, it's more simple to that. Why is he a bad frequentist? Like bad frequentist. Actually, it's a great name for a dog. Frequentist. That's a bad frequentist. Yeah. Well, why is he a bad frequentist? Well, we usually do. You're correct, right? He did one measurement, but usually we have one measurement. But when we do have this one measurement, it's based on simulations, for example, right? On thousands of simulations. And running the simulation, quite easily you'll find out that in 1/36 part of times you get that the sun exploded, you get a bad result. So you need to account for it. Right? So the analysis that the frequentist did here is wrong. He did not take into account a lot of effects. So I hope you liked it, and now we'll go to inference. Let me see. Okay, so I'll skip some of the slides because there's the final part I must get to. Otherwise, I'll be a bad frequentist. Okay, so we have an experiment. We measure random variables. We put them through our estimator.
You have about 15 minutes left.
Well, you took some time for questions.
Yeah, it's true. Maybe 20. 20 minutes.
Yeah, okay. So, experiment, we measure random variables, we put them through the estimator, we get a result. The question is, how confident are we about this result? So there are two numbers to, okay, I'll mention this. This is all a frequentist discussion. In the Bayesian case, we have the posterior probability. So we don't get a number, we get a curve, and from this curve we can calculate our credible intervals. This is how confidence belts are called in Bayesianist. Okay, so the frequentist confidence interval, what does it mean? So let's say you have m equals plus minus sigma m. Or tau equals, I'm not sure what I was thinking when I did these like 3 lines. I'm sure I had a reason to do it, like 1, 2, 3, but I'm not sure what it was. Okay, so you have some measurements, but what does it mean, this sigma, when you repeat your experiment many times? So now again, think like a frequentist. What it means is that 68% of the resulting tau, plus minus sigma intervals, will include the true value of the parameter that I measure. It doesn't mean that in 68% of the experiments the true value is within this range. And it doesn't mean that there's a 68% probability that the true value is in the tau plus minus sigma range. What it means is that if this is my parameter, and now I run my experiment many times, so each blue line is an experiment with uncertainty, 68% of the time it will fall right on, and the rest not. And you can see it here, so this was done with 95%, and there are 100 simulated experiments. So you expect about 5 to miss the right value. And it's roughly about 5 that miss the right value. So again, this is very important. This is the frequentist meaning of confidence belt. Okay, Nyman construction, I really worked hard on these slides. I'll just show them to you so you can wow, but you see it's really, So this explains to you how you construct confidence belt using the Nyman construction. And then I would have explained to you why this is causing a problem that's called flip-flopping, which means that you do not have coverage and that your results are wrong. And then we would have discussed the Feldman-Cousins, which is a different way to do this confidence belts. And then we'll move to type 1 and type 2 errors, and we'll discuss them. Okay, so there's 2 types of error. Type 1 error is when you reject the null when it's actually true. And this is, we call alpha or p-value. And we can choose it to be as small as we want. Type 2 error is when we fail to reject the null when it's wrong. And this is called beta. And 1 minus beta is the power. So this is all just in a table. So if H0 is true and I do not reject it, yay, that's good decision. But if H0 is true and I rejected it, then it's type 1. And if H0 is false and I didn't reject it, then it's type 2. And of course, if I rejected the wrong one, then it's grade 2. Okay, so the first term is significance. It's the probability to reject H when it's true. So let's assume that this PDF is our signal. And I can choose where to put my cut. And I chose to put it here, which miraculously coincide with the green shape here. And this is the significance. So this is the acceptance region. I take everything to the left. And this I threw away. And the amount that I'm throwing away is my how much I missed. And the confidence level is 1 minus alpha. So 90% confidence level means that I'm losing 10%. Now, type 1 and type 2 are related. One comes on account of the other. Because the B error here, you can see that, for example, you can say, okay, so move this line to the right, so alpha will be smaller, but this will make beta larger. So beta, this is the background, so beta is the stuff from the background that enters my analysis that I didn't throw away. So one comes up on the count of the other. And the Niemann-Pearson lemma tells us that the likelihood ratio test is the most powerful test to have for a given alpha. So if you want to get good results for a given alpha, 95%, 90%, use the likelihood ratio test, and it will give you the best power that you can get. And again, go to textbook if you want the proof for that. So here's a graphical explanation of a cut. So I have 2 PDF and I want to make a cut on some value. This is my acceptance region. This is the rejection. And where I put the cut determines how much of the background I put in and how much of the signal I put in. The area to the left is called acceptance region. The area to the right is called critical region. And yeah, so never mind. The p-value is the probability that a test statistic will take on a value that's at least as extreme as the observed value when the null hypothesis is true. It sounds terrible, but what it is, it's basically the tail. If the p-value that I want is more than alpha, we cannot reject H0. And if it's less, we can reject our hypothesis. Now it's, okay, we can also translate it to Z, but I'll skip that. Okay, so let's go back to the likelihood ratio. Let's see what all this blah blah means. Technically. Okay, so here are two likelihood curves. And there's a big difference between them. I mean, in each case, this is the parameter of interest, cross-section, and the y-scale is the value of the likelihood function. So this is just two cases. And the big difference is that here we have a minimum. And here we do not. Now, a minimum means that our fit found an indication to signal. This is the effect that we have here, a positive minimum. Here the minimum is negative, so we throw it away. If when we'll discover dark matter, it will look like this, but only with more significance. It means that we have a positive value of our parameter of interest, and it's strong enough. If I want to make a discovery, now this is kind of going the other way around. If I want to make a discovery, I need to reject the background. This is the definition of discovery. Background means mu equals 0, so the background rejection has to do with where my likelihood curve is crossing this one, this x-axis. So if I have an experiment, I got this likelihood curve. In this case, I'll go to the Z table, I'll translate the one to the appropriate Z value, and I will know my statistics for discovery. In case of a random variable, in case there's no dark matter, and this parameter just is 0, still 50% of the time will have a positive value. 50% of the time will have a negative. So the fact that it's positive is not really big news. The limit we will find by how curvy this line is. So we'll take here a value at a certain point. And you can see that I can only do here one side limit because I don't have this side. I threw it away. Okay, I'm really running now forward. This is an excellent paper. This summarizes all of the profile likelihood and the chi-square stuff. It's a very hard. It's written good. It's language. It's clear. But it's very hard in a way that you need to read it a few times and to really understand it, but it's very recommended. Probably not before bedtime. Okay, so here are just some general thoughts about doing analysis, statistical analysis, and I'll randomly use the xenon experiment, just chose it, to illustrate things. So we can think of 3 methods to do statistical inference. The most simple one is region of interest. Here we do not use likelihood. We just take an area. We say, I expect 10 background. I see 15. Let's check the difference and over the error. The next step is to do a profile likelihood. And we can do it with a simple 1 or 2D, or we can go to many more. And here you see the dark matter results, and the color code is the method that was used. So initially, indeed, it's a region of interest. And then as we go, we get more advanced in time, we're moving to more complicated inference, and this is just for xenon. So basically we have parameters, and we have background and signal, and they're all over the place, and we need to say whether we have signal or background. I just like to point out that the first Xenon 10 result, so there's some limit. But if you read the text, you will see that there were 10 events, but because there was no background model and a way to include the uncertainties, all 10 events were considered as signal, and they were inserted into the limit. So the limit is worse because it includes also the background events. And this is, of course, something that we can avoid in a likelihood analysis. I'm just trying to see what's important here. So the likelihood function, like this is a real-life likelihood function, so there's all the good things that we talked about. So there's a Poisson term, and there's the model term. So you see here NS times Fs, where Fs is the signal shape, NB is number of background event, and FB is the background shape. And then in addition, there are terms that constrained our parameters here. So one of them is the calibration term, and another one, other way around. This is the calibration term, and this one is just Gaussianly constraining. Someone asked me, right, about binning. So this is for you. This tells you how the number of bins, I mean, it's not for plots, it's for the inference, but it shows you how the number of bins can affect your sensitivity. So there's actually, yeah, that's the likelihood function for Xenon 100. The one for Xenon 1 ton I do not put here because it cannot fit on one slide. It's much, much more complicated. Okay, so obviously I have a lot to say. I'm trying to see if there's something here. There are different techniques to handle mismodeling or handle down fluctuations in the background, because if you have lower fluctuations in the background, you might think that you have signal. So there are tools to handle this. And, okay, asymptoticness. Okay, I'll put the slides and you can browse through it. And of course, if you have questions, feel free to mail Marco. We can probably answer it. No, just mail me. I'll be happy to help. So just a graphical summary. So this is how people used to do limits. You have 1.8 background event, 3 observe, the probability to have, to see 3. I mean, the number of events you need in order to get 95% confidence level for 3 events is 4.9. So this is how you do back of the envelope limit calculation. In the modern way, we have those huge codes and numerous computers, and it's getting very, very complicated. And this is how it's done now. And instead of 7.5 million years later, yeah, I'll just put it all. So it's 7.5 million grad students later. So what I was trying to do here is be careful of black boxes. Be careful from just following recipes. Make sure you understand what you're doing. Do a lot of cross-checks. And I think it's important to understand the statistical part of our work. This school is overloaded with information, and the amount of information, at least that I covered, is 2 semesters plus colloquium. So that's a lot. But I do hope that I encouraged you to pick up a textbook and try it yourself, because it's really fun. It's and I used to not like statistics. Yeah, so thank you. And if there are questions,
Thank you very much. Questions?
So just to remind you, now you have the hands-on session, and I'll be sitting in the back catching emails. If anyone has like a question, a private question about inference, feel free, or about the exercise, of course. Yeah, thank you for your attention. I know those days are super long and tiring, but you're doing well.
Okay, so thank you.
Thank you.
So now we have a break.